manufacture with best practices, that we're finding that those best practices are failing, right? So in 2000, I was working at a commercial materials testing laboratory, doing forensic analysis, materials testing evaluation, tensile testing, impact testing. Basically, I was looking at shitty castings for a living. And what became really clear really quickly is that either what I was looking at in the SCM, whether it was an iron sand casting or an aluminum sand casting or aluminum die casting or a copper investment casting, independent of the molding method or the alloy, there was a repeatable feature in the fracture surface that wasn't described or explained in school. So that left me in the conclusion that either I was an idiot and didn't know what I was looking at under the microscope, or everything that I learned at school was flawed, right? And so I started at that time combing the planet to see if anybody was doing anything interesting and new in the topic of casting defects. Came across a gentleman who was doing some work at the University of Birmingham named John Campbell. And so what we're looking at here now is understand that we're in a real unique, odd, bizarre situation where for some reason we've got 50 people from across the continent logged into a webinar, which is hosted by a Canadian who is explaining a technology he didn't develop, right? And so hopefully through the course of this, we can actually get some context that's going to make some sense to people. Any questions that you have, let's get to those at the end, of course. But I think that it would be of huge value if we actually had some, kind of budding questions, because there's going to be some stuff that we need to deal with, and we need to have, healthy conversations about what it is that we're looking at. Most of the stuff that I'm going to show isn't new, right? I mean, it's from either the year 2000 up till now. It was 2000, 2001 when John Campbell codified bifilm theory, and all we've been doing for the last 16 years is putting it into place. Gentlemen like Jim Furness, for example, have been clued into this for probably the better part of 4 decades. The problem is the first 3 decades he couldn't talk about it because he was under NDA, right? And so now we've got a collection of people that have had a theory how to making really good metal castings really, really simple for a long, long time. But we're still trapped in this old mindset where we're not really paying attention to the notion of asking the right questions. So let's see if I can get in and start this slideshow. How's the audio? Everything good?
Yeah, it's very good.
Very good? All right. Very good is good. Share screen, desktop 2, share screen. All right. Can everybody see that?
Yes, everybody's on mute except us, Bob, but we can see it.
Okay, perfect. All right. So today we're going to go over bifilm theory. What bifilm theory is, as many of you probably heard from John Campbell, is the notion that an oxide film gets entrained to the bulk of the melt and serves as the fundamental root cause of most casting defects. The other beautiful thing about bifilm theory is if you can set up an organization, an operation, from beginning to end, operating with the theory if bifilm theory is true, then the processing of this alloy and the subsequent processing should go according to such, which is what I've been doing for 16 years, and especially for the last 4 since I bought this aluminum foundry, which we've set up from the ground up based on bifilm theory. And as you'll notice when we skip back a slide, we are probably the only foundry on the planet that is certified to DNVGL, ABS, Bureau Veritas, AS9100 Aerospace, and Lloyd's Register. And we've accomplished all that within the last 15 months. And we can accomplish this because with an entire team of people that had never worked in a foundry 2 years ago, after I bought this place, I replaced everybody on the floor and everybody in the office and hired all young engineers and quality people that had never worked in a foundry before. The first year we were in operation, I couldn't even use phrasing like cope or drag because nobody knew what that meant. And so we built it up from scratch, 100% based on bifilm theory and teaching a design heuristic and a philosophy that included none of the old voodoo from the old days. So bifilm theory works really, really simple. And let's start it this way. Every time you've got molten metal exposed to air, immediately at that interface, an oxide forms. Depending on the composition of the alloy, that oxide is obviously a different composition. So it's going to be different composition for aluminum, different composition for steel. And some of the steels and the irons, it'll be partly liquid, partly solid. But regardless, as soon as you've got air exposed to molten metal, it oxidizes. This should be extremely obvious to everyone, because for most of humanity, we didn't have metallurgy because these elements were trapped up as oxides and silicates, and they were essentially dirt, right? So it's the onset of the miracle of metallurgy that allowed our civilizations to take a real huge jump forward. A nice allegory that I like to use, specifically when it comes to aluminum, is that it wasn't that long ago when aluminum was the most valuable metal on the planet, surpassing platinum, gold, and silver. The tip of the Washington Monument is made out of aluminum. I don't know if anybody knew that, and that's because at the time the Washington Monument was built, aluminum was the most valuable metal on the planet. Extremely hard to refine, extremely hard to extract. And then the Hall-Heroult process comes about, we get some electrolysis, we're able to use this alloy now with throwaway abandon, where we wrap it on baked potatoes and it's, on our gum wrappers, and we just throw it in the garbage. So over the course of less than 200 years, or essentially 200 years, we go from the most valuable metal on the planet to one that's done with throwaway abandon. Now, the reason why it was difficult to access is because it has a high reoxidation potential. So it serves as the real great alloy to use to prove out these theories, which is the explicit reason why I decided to buy an aluminum foundry, to make great big large multi-ton castings and aluminum and prove that the theories worked. So let's get back to the slide. Every time you've got molten metal exposed to air, an oxide film forms. Now that oxide film that forms grows atomically off the melt. It's in perfect atomic contact with the melt. On the surface that's exposed to the air, however, it's dry, right? If you looked at it under a microscope, it would look like sandpaper or the surface of the moon. And that oxide film is now perfectly electrically inert. It's a ceramic. And so now you've got molten metal with this little ceramic layer, this little oxide film layer floating on the surface that's completely electrically inert. And anytime we have an opportunity for surface turbulence, that oxide film is going to be entrained into the bulk, right? And so what happens now is that oxide film is going to be entrained into the bulk and fold on itself. And so this is where we get the term bifilm, this oxide film folding over on itself. So it's like bicycle or binoculars. It's this oxide film or this film folded up on itself. And this comes in a whole bunch of different forms, and we would call this crumpled up oxide film an unfurled film. Now, let me just see if I can share just my camera. Can you guys just see me now? Was that a yes? Okay, so your microphone's muted. All right, so here's the deal. Okay, everyone's pumping in yes now. All right, excellent. All right, so here's the deal. You guys have all seen this. Anybody that's been to one of John Campbell's lectures, you've seen this a million times, but I want to review it because it's really important moving forward visually. Whoa, what's that? All right. Down here, molten metal. Up here is air. At that interface, we get an oxide film that forms. Any kind of surface turbulence is going to fold in that oxide film. And there's a few critical things to keep in mind. That top surface, dry surface on dry surface, folds over on itself. Dry side on dry side, perfectly electrically inert. Now we've got a pre-existing crack. The other thing that happens is this oxide film, which is entrained into the bulk of the melt, invariably crumples up and also traps a tiny little bit of atmospheric air inside of it, is rolled into the bulk of the melt, and a new oxide film forms instantaneously at the surface, and any kind of any kind of surface turbulence again entrains that. Now we end up with a melt with millions and millions and millions of these little furled up, crumpled up oxide films in the bulk of the melt in suspension. All right. Now, that's strange. Can everybody see me still? Just one person say yes. The first person that says yes.
Yes.
All right, excellent. Good. First time using this program, so we got to make sure. All right, so that's number one. That's an entrainment mechanism. The second, as we're going to look at, is an air bubble. So these are all real simple things. Now, an air bubble being entrained, as we are going to see here, the right image, right? Now we've got a situation where we've got an air bubble rising up through the melt. The interface between the air bubble and the molten metal forms an oxide film. Now, that oxide film that's in contact with the metal is in perfect atomic contact with that metal and really isn't interested in moving so much. And because of the buoyancy differences, as that air bubble rises up through the melt, that top of the air bubble is going to tear and reform, and what's left behind is an oxide film trail in the wake. And that oxide film trail starts getting sloughed off. And what we end up with is a situation where we end up looking like this. Just a quick yes if you can see me again.
Yes.
Yeah.
Perfect. All right, so imagine this. Here's this air bubble rising up through the melt. And we've got this dry side on dry side, and that oxide film, as the bubble's rising, tears off and sloughs off. So we've got this dry side on dry side oxide film. These are pre-existing cracks in your melt, right? And your castings are being polluted with these air bubbles. So we've got two very specific problems with the metal casting technology that's used today. Number one is entrainment of the oxide film that forms at the surface. And number two, the aspiration of air during metal transfer and pouring practices that's resulting in the exact same kind of thing. So we've got real technical things here called bubbles and films, right? Real simple concepts. And these are the fundamental root cause of virtually every single casting defect you can think of. This is responsible for quote-unquote segregation. This is responsible for lamination and delamination defects for the most part. Quote-unquote microporosity, what appears to be shrinkage in the most place, what appears to be hot tear in the most place, and on and on and on and on and on. The belief of most pinhole porosity with respect to gas. All of these things start under bifilm theory to bifilm. Let me click over to the next slide. All right, so here's some example of pouring practices responsible for the entrainment of oxide films into the bulk of the melt. And we can see it as clear as day. Here's a metal entering a mold or a ladle from a furnace, say, or yeah, a ladle from a furnace. And you can see that there's an oxide film at the exposed surface, which then is being entrained into the bulk. And the impingement of a stream of metal into stagnant metal results in the entrainment of air bubbles as well. So what we end up doing is creating essentially this oxide metal pudding that we just keep pumping through the system and messing it all up. Now, this is some SEM work showing furled bifilms in a fully solidified casting. So this is a casting that's solidified quick enough that these oxide films didn't get a chance to open up or unfurl. However, they're still there. So this is what we call the furled oxide film. And you can see as clear as day, if you look at the cross-section of those, and then understand the cross-section of what we're looking at here, these crumpled up features, you can see as clear as day this is what we're looking at, right? Now, this is the same thing, but this is the beginning of what would be called visual porosity or obvious porosity or gross porosity. And you can see in this situation, these are unfurled oxide films or unfurled bifilms. So these are oxide films that were in liquid metal long enough that because of pressure change on solidification and a long solidification time, gas is being ejected during the solidification process, diffusing into the air that's entrained within that oxide film, starting to unfurl them when we get open, visible cracks inside of your casting. Here's a casting, here's some x-ray work on a single casting showing both side by side in the same casting. So you can see the flat areas on this casting, you can see the oxide films as clear as day, but they're furled because that area is solidified quick. Now as we move over to the rib feature, which would have been longer solidifying, you can see that those oxide films have had a chance to unfurl or open up. Now traditional consensus ideology would have called that a hot tear. But what we have here is simply just decohesion within the metallic matrix because there was no metallic bonding taking place. So to explain that, let me explain it this way. Another quick yes when you can see me.
Yes.
All right. The metallic bond works this way, and it's unique compared to the ordered bonding arrangement with the ionic or covalent bond, and it's what gives metals their wonderful properties and allows us to work with them. So here's the way it works. Since I'm aluminum foundry here, I'm going to use the example of aluminum, but of course this goes for any metal. We've got a positively charged cation of aluminum, and it wants to mate. And we've got another positively charged cation of aluminum, and it wants to mate. And if you put two positively charged bodies close to each other, they, of course, would repel. Now, of course, we don't experience metals just self-destructing and exploding everywhere, and there's a reason why. And that's because these two positively charged cations are in this wonderful thing called the metallic bond, which is essentially they are sharing and within a sea or a haze of electrons. And so it's the temporal intermittent sharing of electrons between these two positively charged bodies that are keeping them together. The other beautiful thing about that, since it's not a set bonding ordered arrangement, is that with respect to one another, these ions can move. And this gives metals their ductility, their malleability, their formability, because even though we're changing the location of these, what happens now is that bond can stay present. Now, as soon as we put an oxide film in suspension, which is, again, remember, a ceramic, we can have no electrons sharing across this plane. This is essentially a piece of electrical tape. And so this is an insulator, and we can't have a sharing of electrons across this plane. And so what happens now is locations that are separated by these oxide films is with the application of thermomechanical stresses, they simply decohere. They fall apart, right? And thermomechanical stresses take place during the solidification, the final solidification of the alloy. And what stage does that happen at? So let's review. Metal during solidification goes through 3 separate stages of contraction. 3 and 3 only, right? So we go from, and let me just skip ahead and actually jump back a little bit and talk about jiggling atoms, since it's the most important concept to remember here. So these atoms are in solution, and depending upon the temperature, which is average kinetic energy, we have a lot of motion, right? So when things are really hot, we've got this amorphous material, which is a liquid metal. And because there's no set bonding arrangement, we've got this amorphous situation, and these atoms are jiggling ferociously off of each other. As things cool down, we lose average kinetic energy. These molecules, these atoms start coming closer and closer together, and closer and closer together, and closer and closer together until the point where they get locked into place. That locking into place is the forming of crystals. That is solidification, right? So now we've got a solidified metal. And so here's the stages of contraction that we worry about with solids. We go from a hot solid, right, to a cold solid. That is pattern maker shrink. That's it. That's the last stage. The big stage of contraction is going from a liquid to a solid. That's phase change, so that's what our risers are for. And then the contraction of a hot liquid to a cold liquid, we don't give a damn about. So really, we only care about 2 stages in the design of the casting, right? Phase transfer from liquid to solid, which is the majority of the contraction. And then, of course, like I mentioned earlier, hot solid to cold solid, which is pattern maker shrink, which is the reason why our pattern just scaled up. Now, during the transfer or the contraction from liquid to solid, it's going to happen at different rates within the casting. The thin areas cool first, the thicker areas stay liquid longer. Now, here's something that's really important to keep in mind. During that transfer, or the transition from liquid to solid, the first thing that happens during that lock bonding arrangement is we start to form little dendrites, little tree structures, or the beginnings of these crystalline forms. As those dendrites are growing from the mold wall outward, what happens is they start pushing any oxide films that are suspension forward ahead of the dendritic tips. And as that's happening, these oxide films get a chance to open up, right? Now what happens is that the independently advancing solidification fronts from all directions are doing the same thing. So now the independently advancing fluid solidification front from this side and this side and this side are pushing forward these oxide films. And so what happens is the center of mass, where the last solidification takes place, is where the vast majority of the concentration of these oxide films are pushed. And what happens is now, you know, our customers slice into a casting, there's a large center of mass, and we see a whole bunch of defects there, and we're taught, well, that's because of alloy segregation or impurities in the melt and all of these kinds of things. And for the most part, that isn't true, right? What happens is we damage the metal, entrain these oxide films, and the natural solidification process push the concentration of these oxide films to the center of mass, and then on solidification, these things decohere. So now let's go back to the slide that we were just looking at and understand what we're seeing here, right? So take a look at where the areas where those unfurled oxide films are. Those are the locations that solidified last. So that means that that liquid was liquid longer, that metal was liquid longer, and the oxide films have more of a chance to, you know, open up and expand. There's also a higher concentration in that area of oxide films. And the other really neat thing that happens is that we talked about at the beginning this oxide film being entrained and trapping a little bit of atmospheric air as it rolls in. Going back to the solidification process, and let's just use aluminum since we're talking about aluminum, hydrogen fits interstitially in amorphous or liquid aluminum, right? And what happens during the solidification process is as those atoms move close, hydrogen can't fit anymore until it's ejected, right? And so we're taught that a whole bunch of these little gas bubbles form together to create a big gas bubble, and that big gas bubble is so strong that it pushes apart the metallurgical bond and creates a void in the casting, right? That's a ridiculous and preposterous notion, right? Anybody that thinks about that with an open mind without just being told and believing it will realize that that notion in and of itself is completely ridiculous, right? That's voodoo. That's alchemy rather than chemistry, right? I mean, that's astrology rather than astronomy. These things, this is not a real thing, right? So there's another mechanism taking place. And here's what that other mechanism is. Here's this oxide film that's in suspension, which is furled up and entrained with a little bit of atmospheric air. As that hydrogen is being ejected during the solidification, it's got to go somewhere. Where it goes is it diffuses into the air that's furled up in this oxide film and starts to open up this oxide film. Now remember, these oxide films are also in a location where it's the last metal to solidify, which means not only does it have the highest concentration of oxide films, because the dendritic tip puts it forward, but it's also going to have a much higher concentration of hydrogen because the hydrogen had to go somewhere because it was ejected during the solidification process. And now what also happens is that we get these isolated pools of molten metal in these regions because the feeders start to freeze over on the top surface, and so we lose all our metastatic head pressure. And so you add those three features together, what happens is these oxide films unfurl, open up, and create what's traditionally or nominally known as a hot tear, right? Now going back to the slide that we were just looking at, that defect on the left where it says unfurled oxide film, that would be called a hot tear. Now this casting is a stave for a cooling stave for a nuclear reactor. I did the engineering on this. This is a nickel aluminum bronze 5 or 6 years ago. And these were the parts that were pulled out of the reactor. And so these were in there for about 30 years. So these are castings from the early 70s, right? And so the customer did not want castings that looked like this again. So we re-engineered with the proper filling system and produced castings that were absolutely perfect and completely free of those defects. Now, we have evidence of this in the real world, and every foundry that pours non-ferrous metal sees it every single day. And we've got a test that's part of our industry standard that has been set up for the exact wrong reasons, and we're looking at the wrong things, and leads to the industry, again, using misnomers. So that's the reduced pressure test, right? So what we're looking at here is, and if everybody doesn't know what the reduced pressure test is, basically what you do is you take a little bit of metal, you put it in a cup, and you let it solidify under vacuum. And the idea is any gases that are present that solidify under vacuum are going to create porosity defects in the casting. So the casting is going to look like, the little casting cup, metal solidifies, looks like a muffin top. We'll do a density evaluation, those kinds of things, and determine whether or not there's a problem present. So here's how we can prove bifilm theory. So here is 2 cups, 2 tests. The one on the left was poured in the test cup and allowed to solidify on the test bench under atmospheric pressure. And the one on the right solidified under the vacuum. The one on the left, as you can see, has furled or compacted oxide films. They just haven't had a chance to open up, but you can see them that they're there as clear as day. The one on the right, which solidified under a vacuum, which now allows the gases to diffuse into the oxide films, has a pressure drop when the skin forms and allows the oxide films to unfurl. You can see that as clear as day, that's those crumpled up oxide films just opening up and unfurling, right? And so a lot of people call this the gas test. So what we're really looking at here is an unfurling of oxide films, and we're duplicating what's happening in the real world. Now let's juxtapose the test parameter with the real casting, right? So on the right, you can see the sample that's solidified under air with pressure corresponds virtually identically to the sample that's solidified quickly. So we don't have an unfurling of oxide films. The areas that solidify slowly or have the unfurled oxide films look exactly identical and correlate exactly identically to the sample that's solidified under the jar with no atmospheric pressure, right? We can see that correlation is clear as day. And back to the original slide, on the left, you can see those compacted furled oxide films in the area that solidified quickly. And the area that solidified slowly, the oxide films start to open up. These are all the exact identical things that we're looking at here. All right, so that's the entrainment of the surface. I think we can understand that as clear as day. If anybody has any questions, butt in now. Here's what happens when air bubbles start entering your casting cavity. Metal casters for generations have known that during the pour, air is being aspirated. Most foundries, you can hear it. You can hear the gurgling, the slurping, the popping. Traditional wisdom has been, as long as the air bubbles have a chance to rise through the melt and they escape the surface of the melt and that we don't have a pre-solidifying skin, we're going to be okay. Traditionally, what's happened when castings have subsurface porosity, foundries will just pour the casting a little bit hotter, and their theory was that'll get rid of the bubble. And while it got rid of the tiny little bubble deposit at the surface, which we'll look at in a second, it did nothing to change the fact that the casting was completely damaged. In this image, what we see is the ingate of a casting and air bubbles rising up through the melt. And behind that air bubble is that oxide film trail being left in the wake like we looked at and we talked about. What you're going to notice now is this is the generation, the creation of millions of multiple leak paths through the entire cross-section of your casting. These pop up when we do hydro tests and the casting starts to weep, and then you do liquid penetrant inspection and you can't even see it. So the inspector just circles it with a hole. You send a picture to the foundry, and the foundry says, what the hell did those idiots do? There's nothing wrong with that casting. Maybe they just made a machining error and they're trying to lie to me. And then everybody starts fighting because the foundry shipped a shitty casting, right? This is that air bubble rising up through the melt. You can see the cross-section of what that oxide film trail would look like. And again, it's a tube with air on the inside, oxide on the outside, preventing metallurgical bonding, and perfect pre-existing cracks throughout your entire melt. Can everybody see this video? One quick yes. All right, I'll assume the answer is yes. Hey, Jerry, give me a thumbs up if you can see the video.
Yeah, we can see it.
Perfect. All right. This video is from the University of Birmingham in 1993. And this is live video X-ray work that was set up by John Campbell. And the purpose of this was, let's figure out what the hell's going on when we're pouring a casting. And you can see when we're watching this video, the vast amount of air, I'm going to play it again, that is aspirated during the pour. And all those air bubbles that you see rising up through that melt are leaving an oxide film trail in the wake and resulting in a perfect pre-existing crack through the metal. When John saw the results of this experiment in Birmingham in '93, he says it was his eureka moment, and it's what set the progress to only 7 years later codifying bifilm theory in late 2000, early 2001. Here's some work that was done in Canada, doing some water modeling, showing virtually the identical thing. Water modeling is great because the kinematic viscosity of water at room temperature is near identical to our engineering alloys at their pouring temperatures. And what we're showing here is essentially what we would call our discharge coefficient. So of the material being poured, how much entering the casting cavity is air versus metal. And this showed between 30 and 50% of the volume of material entering the casting cavity was air. And you guys will notice that anybody who uses that preformed ceramic tube gating, this is exactly what you're doing, is you're depositing between 30 and 50% air into your casting cavity. And all of that surface turbulence from the transfer, all of the air aspiration from the rough turbulence, and then all of the air bubbles are making an oxide metal soup that we want to turn into a casting. Now, let's get back to this air bubble rising through the melt. We discussed the fact that foundrymen have decided, well, let's just make sure we pour a little bit hot so at that surface we don't get a pre-formed solidification skin so that we get air bubbles below it. And they look at something like this and say, hey, and I'm going to play this again. You can see as clear as day, as soon as the bubble passes through and it's gone, we don't have to worry about it, it's gone, right? It's not in the melt. We don't have anything to worry about. And that was a critical flaw in thinking way back when. And we can illustrate this using some computer simulation and show how disgusting this really is. So here's what we're looking at. Everything that you see is blue is liquid aluminum. Everything that's red is air, atmospheric air, right? So you can see the air-metal interface at the surface, and you can see what's going on with the bubbles. You can see rainbow-colored features, which is a combination of metal and air, which is oxides at varying thicknesses. This simulation was done for me by Sam Scott at ESI. He's been my partner in crime for like 10 years. So I have to give props to Sam for being able to put this together for me. What we're looking at here is only 2 bubbles in liquid aluminum, and let's take a look at what happens. You'll notice instantly we get microscale turbulence and vortices at the shear zones. You can see the air being consumed and turning into oxides. You can see that what happens now is that as the oxides are being consumed and getting thicker, they become neutrally buoyant and trapped in convection currents. You can see on the surface now what we've got is an oxide film against an oxide film. And so now we've got, like a surface lamination or an orange peel type defect. And you can see now from those 2 little air bubbles, we've got literally dozens and dozens and dozens of small little locations of non-bonding within our metallic matrix. And this is from 2 little air bubbles. Forget about thousands and thousands and thousands of them during the life of the core. During the solidification process, we talked earlier about those advancing dendritic tips pushing the oxide films into position and creating heaps of them. So that's that type of thing. Here's some example of individual grains of sand being trapped within an oxide film on a fracture surface of a casting. And actually, let me explain this morphology for a second here. Jerry, thumbs up when you can see me.
We can see him.
Perfect. All right. The oxide film starts at the surface of the melt. During our poor turbulent filling practices, what happens is that oxide film gets rolled into the melt and starts hop skipping through the running system. Now, keep in mind, let's look back at the morphology of this. Dry surface on dry surface. The back of this, which is in perfect atomic contact with the melt, is sticky, like flypaper, you want to imagine. When this is furled up and rolled over on itself, you've essentially got dry surface on dry surface crack and a sticky side on the one surface. Now we run through this turbulent running system and we bounce and skip these through, and any loose grains of sand or dirt or dust, what happens is they're going to get stuck on these oxide films, and then as the oxide films are floating in suspension and pushed into place by the advancing dendritic tips, the grains of sand are stuck on the oxide film, and that's what we were looking at on that slide, right? It's the only explanation for why there would be grains of sand in a casting, because even in aluminum, there's an order of magnitude density differences between silica sand and the density of aluminum, right? 3 orders of magnitude when we get to the ferrous alloys. And so there's no explanation as to why our customer machines into a casting and finds a patch of sand, until we realized that that sand was stuck in these oxide films. And now when we go back to the slide, you'll notice as clear as day that we've got a bag of oxides with grains of sand in it. Now, anybody that's pouring the nickel, aluminum, bronzes and ferrous alloys will always have these great big, large, disgusting defects in the cope side of the casting. Those are agglomerates of millions of little oxides, and this is the morphology, or this is how it takes place. You guys can see this video, Jerry?
Yes.
Perfect. This was an experiment that was done on the International Space Station to show the rapid kinetics of particle agglomeration. What you're looking at here is sodium chloride crystals in a bag of water in microgravity. And you can see that as these little crystals or oxides form, in our case, they really quickly form these large floccules or agglomerates. And this is what's responsible for these great big, large, disgusting defects that we see in our ferrous alloys in the cope surface. They agglomerate really quickly, float to the surface, and then we have an absolute nightmare we have to dig out. These will be called colloquially in the steel foundry snotters or seroxide defects. Now here's some examples of fluid flow practices that take place inside of all castings that are made according to traditional means. Anytime your metal has an opportunity to drop within your casting cavity, it looks like this, right? So if you're gating at the parting line, it falls. If anytime your metal falls within the casting cavity, it's doing this kind of thing, where blue is the metal and every other color is a combination of metal and air. Every separation and recombination of a droplet, you're loading in oxide films and introducing pre-existing cracks into your melt. The sprue well is this, and you can see what we're doing is we're aspirating air bubbles and oxide films and creating a pudding that then we hop, skip, and jump along a running system and then deposit into your casting cavity. any filtration that you use in the system, well, look what's taking place beneath the filter. You're basically creating a real horrible, nasty situation beyond the filter. So you've got terrible pouring practices before the filter that plug the filter, that slow down your pouring rate. And then as the metal squirts through the backside of the filter, what you're doing is creating a whole bunch of droplets and resulting in a giant mess. The guys that sell us our filters love this because now they end up telling you things like, well, you should really only put 50 pounds of metal through a square inch of filter, blah, 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 all this stuff. Let me tell you that none of that is true. So here I will pour 10,000 pounds of aluminum through 60 PPI filters. There's no slowdown, there's no change because my filters aren't filtering. I'm using the filter as a throttle, it's only for friction. And if any of your casting systems are using a filter to filter, you've already done everything wrong, right? Now let's go over and start looking at some gating technique. So what we've got here is the traditional AFS 1:4:4 gating ratio. So this is what we're taught at the Gating and Rising course to use for non-ferrous alloys. And so we've got some traditional features. This is a conical pouring cup, which is essentially an enlarged targeted entrance so that the ladle man can hit it. We've got a sprue, which has nominally been usually randomly tapered just so that we can remove it from the sand. We've got a sprue well, which the idea is it's going to cushion the metal from the fall. And I love the fact that we've even got calculations on what size the well should be. And then we've got a runner, right? And so the 1:4:4 means that at every opportunity for a metal transfer or transition from one feature to the other, we have an expansion of cross-section, right? So in this case, the runner is 4 times the cross-section of the sprue bottom, and then the gates are 4 times the cross-section of that again, so we just keep expanding. And so what ends up happening is with these expansive runner ratios, we run into a whole bunch of problems. So let's take a look at this slide, at this simulation running. The temperature, the color gradient in this simulation is temperature. Let's take a look. First thing we're going to notice is that there's a very strange temperature fluctuation taking place in both the pouring cup, the sprue, and an obviously very poor temperature thermal distribution within the runner itself. Now, for that temperature fluctuation within the sprue itself, that's clearly because we've got some volumetric displacement issues, right? If this whole thing was completely full, we'd expect to see that temperature gradient being equivalent, equidistant or nominally exactly the same. So let's take a look at this exact same simulation. We'll slice it longitudinally down the center and change the viewport to fluid volume. So what we're going to see in this version of that exact same simulation is everything that's red is metal, and everything else that's not red is a combination of air and molten metal at various stages. Now, what you're going to notice instantly is that conical pouring cup is a perfect aspiration pump. Gulp, 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 gulp. And for the entire life of the pour, it's sucking in air bubbles, and air bubbles, and air bubbles. And you can notice at the end of the runner is not full. And so now we've got air bubbles, air bubbles, air bubbles. And now we run into a whole bunch of problems. And we run into a whole bunch of issues that are poorly explained in industry. And let me use this section to explain them. Jerry, thumbs up when you can see me.
I can see you.
Beautiful. All right, so here's the deal. When you've got molten metal flying through the air, which basically means it's leaving our ladle and moving towards the pouring cup, gravity is accelerating that falling metal. Gravity is accelerating it at a predictable rate. The air immediately adjacent to that metal is also increasing in velocity because of its proximity to that falling stream. Now, there's an obvious inverse relationship between velocity and pressure, meaning that as the velocity of the air is increasing, the pressure decreases. Now, the air over here, not immediately adjacent to that metal stream, now has greater pressure than the air adjacent to the stream, and so it pushes its way in, and that creates an aspiration mechanism. This is a perfect pump, right? Bernoulli knew this. And so what happens now is create this perfect pump, gulp, 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 gulp. Any of us that stayed at a creepy, gross Holiday Inn have lived through this because you're having a shower, and their cheap little shower curtain starts pulling up and sticking against you, and you don't know what the hell the person in that shower did before you. You don't know what they wiped on it, what they didn't wipe on it, and it's disgusting, right? A lot of us think that, that's because of static cling or something, but that's not what's happening, right? What's happening is the water's flying through the air. The air that's immediately adjacent to the stream is losing pressure. The air on the outside now of the shower curtain has greater pressure than the air on the inside of the shower curtain. And so it pushes the shower curtain up against you and you get the heebie-jeebies and you feel real gross, right? Let's not even get into soap. I mean, when you use a shower after someone, are you supposed to wash your face first or the other stuff first? You kind of have to do a calculation to guess what they did last, right? But I mean, that's a conversation for another day. So let's move on. Now, here's what happens is now we've got metal and air running through this running system and this mold. All of the cavities inside the mold are air. I mean, we can understand that, right? Most of us use silica sand or some kind of other sand, but let's just say silica sand because that's the sand that's used the most. And as soon as you start taking round or semi-round or semi-angular grains and start packing them together, you only get a certain packing factor, 60, 65, 67%, which means that the other 20 to 30% is open space. And we understand this, and we call this the permeability of our mold. Now, those individual grains of sand are mixed in a mixer and completely coated with our binder. Most of our binders are plastics. They're petroleum byproducts. And so now we've got a grain of sand completely surrounded by a plastic and another grain of sand completely surrounded by a plastic, and they're stuck together. And they're stuck together in a 67% compact ratio with a whole bunch of extra air in them. And this is what our mold is made out of, and this is what's actually holding this mold cavity open. Right? So let's talk about the runner. The runner is an empty space, or essentially think of it as a tunnel inside of our mold, and our mold is sand held together by plastic. Now, we've got air, and we've got plastic, which is a beautiful fuel source, and we've got heat from the molten metal. And to have combustion, you need three things. You need a fuel source, and you need oxygen, and you need fuel. And so let's repeat. The binder is the fuel, and both the spacing in the sand grains itself and the air in the cavity is oxygen, and also the air that's mixed in with this hot metal is also fuel, and the metal itself is the heat source. And so now what happens is when we've got a running system that's not full, what happens is this. The metal comes tumbling through this running system, and it pushes up against the mold surface at the top of that runner. And when it does that, it pushes hot, boiling hot, super hot air through that running system, and we create like a bellows effect. And every time we're blowing this hot air up through this void, we start combusting the binder. And when the binder combusts, it burns away, and those grains of sand fall into the metal. They fall into the runner. And the runner is empty and full, and empty and full, and empty and full, and empty and full, and empty and full. And so what happens is we just keep wearing away and eroding all of the sand. And so what happens now is all of the castings that are poured according to traditional methods, you will shake them out and you will see that you get erosion, right? You get erosion at the sprue base, you get erosion in the runner, you get erosion in the cup. And people will say, well, shit, that's no good. Maybe we should put some coating on there. Maybe we should pour a little bit less. Let's lower the coat height because we've got so much pressure that what happens is that we're getting a whole bunch of deterioration of the mold. None of those things are true, right? Because what happens is, if you've got no combustion, the sand can't break down, and the binder's not going to burn up, and you're not going to get grains of sand. And furthermore, if you can create a running system where the metal is pressurizing the running system itself, nothing can fall in it. And we're going to see slides that show that here in just a second. All right. On to this. This is live video X-ray work, now skipping forward, 1997 at the University of Birmingham. And the concept was really simple, and the concept was this. We have an understanding that in training the surface oxides into the metal is a bad thing. The aspiration of air bubbles into the metal is a bad thing. And hop, skipping, and jumping metal in an empty running system or an expansive running system, which ends up in an empty running system, a non-filled running system, results in a bad thing. So what if we did this? What if we calculated, as that metal is falling, the exact taper that that metal takes due to the acceleration due to gravity? And let's review why this is. At a consistent volumetric flow rate is a product of two individual variables, right? Cross-sectional area and velocity, right? So area times the velocity equals our volumetric flow rate. Or areas in inches squared times velocity in inches per second squared equals cubic inches per second. I'm sure we can all understand this, right? Q equals AB. Now, at a consistent volumetric flow rate during the pour, gravity is accelerating the melt as it falls, which means that the area has to be reduced at an extremely predictable rate. So what if we calculate that exact taper and provide only exactly that shape for the metal? which means that now we're hugging the metal in place as it's falling and not allowing any opportunity for it to splash, jump around, not allowing any opportunity for air to be aspirated. Think of it as putting a straitjacket on a crazy man. We're hugging that metal into place, not allowing it to do anything. Then we're going to transfer it at the bottom smoothly into a runner that has the exact same cross-section again. So now that we're pushing the metal into that cross-section, the metal doesn't have a chance to splash or roll on itself. That surface can't be entrained into the bulk of the melt. And then what we're doing is we're creating a system where we have a metal over air system where we're just pushing the air forward, and the air can never get into the bulk of the melt. This happens in your body every single time you take a breath. And when it doesn't happen, we have an embolism and we die. Right? We have an understanding that, you know, air in blood is bad, water in your breath is bad, and our bodies do this naturally. The branching process of your circulatory system does this, from your aorta, you know, to all the major arteries, to all the small little arteries. I mean, it just continues to shorten down and shorten down and shorten down, and the total final cross-section is the same as what you started with. And so this is exactly the same thing we're going to be doing with the deposition of molten metal into the casting cavity. So let's take a look. So this was the first attempt at designing by volumetric constraint, or what is now known as the naturally pressurized filling system. And you will notice within the running system and within the casting cavity that we have no air bubbles, right? Now you can see that there's a ton of turbulence as the metal's entering the casting cavity, and we'll get to that later. But what we know now is we can drop metal, drop it vertically, transfer it horizontally, without the entrainment of air bubbles or without the entrainment of bulk surface turbulence, which rolls in that oxide film into the bulk. Now, this was done by putting the nozzle of the ladle into the mold, so we still didn't take care of the pouring cup problem, and we haven't taken care of the velocity problem as the metal's entering, because you can see, let me replay that one, that as the metal enters the casting cavity, that we've got a whole bunch of surface turbulence and we're rolling metal on metal, so that's a problem. Well, we can get rid of that later, but within the sprue and the runner itself, you know, we've got some success. So this was the beginning. This was 1997. All right. Here we go. On the left side, AFS 1:4:4 gating ratio, conical pouring cup, randomly tapered sprue well, expanded ratio, runner geometry. On the right side, very simple little design. You know, it's got some issues. We still got that square corner in the bottom, but let's just take a look. In this simulation, you're going to see velocity vectors showing the direction and magnitude of the flow. Actually, this one doesn't have the vectors. The next one will. What we'll see instantly, however, is that both of these are still running live if you look at the timestamp on the top right, although the one on the right looks like a photograph because it's in perfect equilibrium. You notice that the metal, the surface of the mold, so in the runner, it's not even moving, right? So basically, we've got no potential for either the mold to get into the metal, air to get into the metal, gases to get into the metal, none of these kinds of things. And on the left, you can see that huge velocity fluctuation still taking place, which obviously means we have pressure fluctuation, which obviously means we have pressurization and depressurization of the metal, hence depressurization of the mold cavity itself, which results in that aspiration mechanism and mold decomposition issue that we talked about. This one will show velocity vectors. Look what's happening in that sprue well. And then look what happens as the metal is jumping along this unfilled runner. See that rolling back wave? See those pockets of unempty space? You see how the metal rolls back on itself, entrains the oxide film, pushes up against the surface, which is pushing that air through as a bellows action. This is a complete mess, right? It's disgusting. Now, both of these are still running live. And the one on the bottom is a perfect equilibrium because we've just got a beautifully, perfectly controlled filling system, right? No surface turbulence whatsoever, which means no bellows action, no decomposition of the mold, nothing can get in. We've got perfect control of the metal. Very simple manipulation of the metal using simple geometric manipulations. Here's what happens in the runner that's not full. Metal is hop, skipping, and jumping, rolling oxides and air films into it, producing a disgusting pudding. This is what we want to happen if we design using geometric constraint. The advancing metal front has an oxide film with the exposure to air, which is tearing and reforming and tearing and reforming and tearing and reforming. However, when it tears, it gets laid down between the metal and the mold as this interfacial oxide film. Think of it as like a tank trap, right? So what ends up happening after that first pass now is the metal is actually riding on an oxide film and never touches the mold, right? And what happens now is we've got metal pushing all the air forward. So we've got beautiful, beautiful setup where even if there's dirt in your runner because something broke off when you close the mold, the metal's just going to run over it like an ATV and an Argo, like a tank trap. It's not even going to matter because it's not going to get in the melt because the metal's just going to run right over it, bump, bump, just like it wasn't even there. And now we have an opportunity to start creating beautiful castings. Here is a runner section snapped off and put in an SEM to show that interfacial oxide film and show that that theory works. You can see the oxide film and the individual grains of molding sand. Now, let's have a conversation. Let's put our big boy pants on. So the reason why the non-pressurized gating systems came to be, and the reason they came to be used for the non-ferrous alloys, is because the non-ferrous alloys are the alloys that have the highest potential for reoxidation. We all know this. Nickel, aluminum, bronzes, aluminum, magnesiums, they're all sons of bitches, right? What happens is with the exposure of air, the oxides are rigid and they're fast forming and they suck. And so we realized that if we're pouring fast and we're squirting metal, that gives an opportunity for these oxide films to form. And so the progenitors of the non-pressurized gating system thought this: let's slow the metal down. If we slow the metal down, it won't squirt through the gates and will result in less in-mold cavity oxidation. And guess what? It kind of worked, right? It kind of worked to the huge detriment. And it kind of worked because it's, again, what we talked about, it's a manipulation of the continuity equation, this Q equals AV thing. You've got a consistent volumetric flow rate, and you've got an expansion of cross-section, which has a reduction of velocity, right? And if let me just skip back a few slides. And you're going to see that in this one, right? So notice on the left, the 1 to 4 to 4 non-pressurized system. The one on the right, designed by geometric constraint. And you're going to notice that in the runner itself, that the metal is traveling much, much slower than it is on the one on the right, right? Much, much slower, but to huge detriment. So let me skip forward. All right. This brings us to a simple thing. We can't slow down the metal by expanding the cross-sectional area because that results in the entrainment of oxide films, surface films, air bubbles, sand from the mold, decomposition of the mold. Everything starts falling apart, and we've gone to hell, right? The problem is now we've got to deal with the velocity issue. We know how to deal with turbulence if we design by geometric constraint and only allowing a perfectly designed pathway for the metal so that we're hugging it into place. We understand that's the case. We know that the conical pouring cup is a disaster. We're going to take care of that in a few minutes. We've still got the issue of velocity to deal with because we can't use a naturally pressurized fill system and reduce velocity by manipulating cross-sectional area, not in the way that it was done. And so now we have to realize that we've got a velocity problem to take care of. And so this is simulation, the exact same geometry, running at 4 different velocities. And from everything that we talked about so far, we will realize that the one on the top left is probably okay. We don't have any surface rolling on itself. The one on the bottom right is most certainly crap, right? Just rolls back on itself, just a terrible, horrible mess. But what about the one on the top right? What about the one on the bottom left? Right? How fast is too fast? And surely there should be a scientific explanation and a scientific reason for why that is. And of course there is. So we realized really quickly that it's the surface of the melt that was exposed to the air that we don't want as part of the bulk of the melt. And so do we have any examples in nature of liquids with standing gravitational acceleration and not entraining their surface into the bulk? And of course we do. And we see it every single day. And this is the pendant and the sessile drop, right? And so what happens is, a yes when you can see me?
We can see him.
Beautiful. All right. So here's the deal. We've got a droplet of water. And in this case, let's go straight to a droplet of aluminum. Take a droplet of aluminum, put it on a non-wetted substrate. The surface tension of that liquid will withstand gravitational acceleration to a certain height. If you go on the floor of any foundry and start picking up droplets that were spilled, it doesn't matter if it was 2 millimeters in diameter or an inch in diameter, compare the heights of those droplets, they're going to be the same. That's because the surface tension of that particular liquid is able to withstand gravitational acceleration. When you get higher than that droplet height, it gets squeezed down and ruptures. And so the really beautiful, interesting thing we can do now is start actually using some science to understand what's happening here and apply that to what we're doing with metals. And we're going to use the sessile droplet to do that. So here's a droplet of aluminum on an unwetted substrate. We can measure the height, it's 412 thou. We can calculate gravitational acceleration offered upon that droplet and find out that the surface tension of this liquid is able to withstand 17.8 inches of velocity before the surface tears, which is extremely important to consider, because now, if the metal is traveling less than 17.8 inches per second, that means as the metal is traveling, it's being held in check by surface tension, which means that the surface isn't tearing and you can't get the oxide film into the bulk. So this is what we're going to call now a naturally pressurized surface tension controlled fill system. Imagine now if you can start depositing into the casting cavity molten metal that has no air bubbles, no entrained oxides from previous, and as it enters the casting cavity, it's being held in check by surface tension. So now what we're doing is expanding a big, beautiful ball of molten metal into the casting cavity. And as it comes up against that mold surface, what happens is we just lay oxide against mold. And what we're doing now is we're expanding this big, beautiful ball of molten metal into your cavity. And the molten metal is separated from the mold by an oxide film. And you get beautiful, wonderful surface finishes that have never believed to be attainable. Surface pinholing porosity goes away, and it really, truly works in any alloy. All right, so we know the speed that we need to maintain once we enter the casting cavity. Now we've got a serious issue, because if you notice, that drop height is only 412 thousandths of an inch, which means if we're dropping metal more than a half an inch, we've already screwed it up. For most of the castings, let's say for a 3 feet tall or a 1 meter tall casting, by the time you're in the runner, that metal's traveling about 200 inches a second. So we've got to go from 200 inches a second through the gates into the casting cavity at less than 18 inches a second. That's a tall order. That's a tricky thing. So we'll talk about that in a second, but let's go back to that terrible conical pouring cup. Here's the idea. It is the stream of metal falling in to the hole of the sprue that results in the aspiration mechanism. So the simple task is to create an offset situation where we're going to convert and translate our vertical velocity component to a horizontal velocity component and arrest it, and then hopefully restart it. So what we see here is water modeling of an offset step basin. Can you guys see the mouse on the screen? Probably not at this point, right?
Yeah, we can see it.
Oh, you can? Okay, excellent. So the metal comes out, we got a vertical velocity component, hits the bottom, starts transferring to a horizontal velocity component, hits the wall, this wall, that wall, this wall. And here we've got a little step, and it hits that step. And what happens now is the idea is we're going to have any kind of turbulence from the drop here get arrested. We're going to have an opportunity for detrainment to take place, and then we get to start the metal entering the sprue at essentially zero velocity. And then the velocity will be determined by the height of the metal in the basin, right? The idea is let's prevent an aspiration mechanism, and let's provide an opportunity for detrainment of ladle slags, those kinds of things that might enter the system. So let's take a look at how that works. So you can see the first few seconds of filling that there's tons of air, but now when the system is primed, you can see that no air or almost no air is entering the system. Now we got a little bit of a choke, and this is straight sprue. So you can see that there's obviously flaws, but you can see what happens now is if we create a location where we can have a reduction or basically an elimination of that vertical velocity component, what we do is we provide an opportunity for the reduction of the aspiration mechanism. And now what we've taken it to is a prevention of the aspiration mechanism, which is I'm going to show you next. Here's computer simulation showing exactly what we were just talking about. So this is in a fully primed basin. The color gradient that you're looking at is velocity. And you can see that what we're doing is we're arresting and separating that velocity component and restarting it again at the sprue entrance. This gives us, again, perfect control and design of our fill system prevention of the aspiration mechanism, and an opportunity for detrainment. And what I mean by that is any ladle slags now that are dropping in, that are forming in the edges of your ladle that happen to make it in and fall off into the stream, what happens is they're going to hit that basin, the basin is full, and they're going to stay floating on that surface. And any that make it subsurface, they're going to have a chance to float out right away because they're not getting pulled down by a stream that's sucking it right down into the sprue. So let's take a look at what a nice proper pore should look like in gravity. And you're going to notice this feature here has got a stopper in the basin. And the stopper is to prevent that first metal that's falling into the basin that has a little bit of entrainment of oxides in air from getting into the casting cavity. So let's take a look. So we're going to fill up the basin. Everything is quiescent. You remove the stopper. And you'll notice now we're not pouring that casting. Gravity has created a pump. We've created a gravity pump. And we're not pouring metal into the hole anymore. And I hope everybody can understand that, right? So what we've got now is we've got set up a situation where this entire pathway that the metal has to fall is completely naturally pressurized, so that there can be no splashing whatsoever. And we've created a situation now where what's filling and providing the opportunity for the metal to fill and controlling the fill rate and all these kinds of things is the height of the metal above the sprue. And with the ladle man, all he has to do is keep the metal filled offset to that. Now, as that metal is falling through the air, entering the basin, there's an oxide film that forms on the stream. However, as it hits the surface of that filled basin and plunges below the surface, an oxide film gets stripped off, just like wire strippers, right? And what happens is you get this big bubble and foam of oxides that are kept at the top of the basin and are never allowed to get into the melt. And you're going to notice, let me play that slide again, that we're not pouring the casting because we'll stop, quote unquote, pouring before the casting is filled. And all we're letting happen now is we're using gravity as a pump. We fill the basin, we stop, casting's still filling, and we just create a balanced situation. Nice and quiescent. You can see how beautiful and clean and smooth that metal is. And we've created a gravity pump. And you can see on the basin all those oxides that have built up. Now, here's another example of a larger pore. And pay attention to the marshmallow of oxides that get built up and stay on the top of that basin. Pores off to the side, arresting of the vertical velocity component, transferring to the vertical velocity component. Look at that big, giant marshmallow of oxides. I know this video is not the clearest, I'm going to play this again. In castings that are made according to traditional methods, all of those oxides end up inside the casting. This simple mechanism, this simple technique prevents that from happening, and all of the oxides stay at the top of the basin. And you can see that's only after a couple seconds. On a long pour, and some of the castings that we do 5, 6, 7, 8, 9, 10, 11 minutes, it gets to the point where those oxides are almost falling out of the basin. There's so many of them. Right? All right. Back to here. All right, so let's review. Oxides that were generated at the surface of the melt that are entrained due to bulk turbulence are bad. Air bubbles inside of your casting are bad for the exact same reason. Because of these unpressurized gating designs, what we end up creating is a situation where we are using the molten metal as a heat source, the binder as a fuel, and the air is the oxygen required to create a combustion mechanism. And so we can start piecing together virtually every single defect that takes place. Let me show you a wonderful slide. And when we're doing these kinds of things with respect to the advancement of technology, it's always super, super important to look at it with an eye that pays homage to the past, right? Because emergent technology is everything that's required to produce some kind of result that is successful. Now, let me just find the slide and take you guys back there. All right, Jerry, can you see that?
We can see it.
I got this nailed. Boom! All right. So this is from a study that was done in 1987 by the Steel Foundry Society of America. What they did is they took 500 castings from 14 independent foundries and did full cross-sectional microscopic evaluation to determine the inclusion content. And here's the results. In excess of 83% of the defects found in these castings were reoxidation defects. Well, holy shit, who would have thought, right? A recombination of molten metal and air and trained into the bulk of the melt. 83%. All right, let's move on. The vast majority of the rest of the defects are mold inclusions in your casting. Well, we talked about that already. You can't get mold into your metal if you don't allow it. Slag defects, well, we can prevent that too. Refractory defects, that's the same kind of thing. Deoxidation byproducts, well, that's... So what you end up seeing now is if we take the very seed of bifilm theory, which is a real simple theory, and start applying it to the engineering parameters and design heuristics with which we operate in this industry, we can eliminate all of these casting defects, and guess what? It's true. And it happens every single day. It happens every single day here. So you can see now that if we take a look at biofilm theory, and if we start applying it across our operation, we have now a responsibility to start taking a look at every single thing, every single sacred cow that we thought was true, every single practice that we, operate on and believe to be true. And then we start looking at things like, well, what about casting in a vacuum? Well, that's silly because there's no real vacuums on Earth. There's almost vacuum. And with terrible pouring practices, which most vacuum casting practices have, you're still going to entrain oxide. I'm sure they're thinner. Then you're going to say, well, what about these super alloy, turbine blades and stuff that produce really great results that don't fall apart? Well, those are made using a single crystal practice, and they are good castings not because they're single crystal and have no grain boundaries, but because as that grain grows, it just pushes forward with those advancing dendritic tip all of the oxides to the surface. And what you're left with now is a perfect metal. So what about intergranular corrosion in stainless steels? What about sigma phase and chi phase and super duplex stainless steels? What about all of these things? Once we start piecing them together, we start making sense and understanding that the root cause of these defects are bifilm theory. Now, let's take a look at the degassing practice, quote-unquote degassing practice for aluminum, for example. So we have a bath of aluminum. It's believed to be completely contaminated with quote-unquote air bubbles of hydrogen. And so what we do is we take a graphite shaft, we stick the shaft down, we put argon through the middle, and what happens is we bubble this through and all these little bubbles float out, and the theory is that those bubbles of argon stick to the bubbles of hydrogen and pull it all out, which is crazy time. It's crazy time, right? What's happening is we are actually lifting these oxide films to the surface, whichever ones we can. But then we also end up creating another real horrible situation because most of the compressed gases that we use have some water vapor. And so we're removing these large oxide films from the melt, but we're creating millions and millions and millions of little ones, which is why if you take a look at the rotary degassing practices, nobody can ever come to any kind of consensus on how long it should be, what kind of rotor designs it should be, how long it should go, because as you're removing the big oxides, you're creating millions of new ones. And so you get to a point where you actually peak off. Well, here, the properties were great here, and then they started to drop again. So, and now we get to something, for example, like titanium boron grain refiners. Well, the belief is let's throw these things in, they're going to mix in, they're going to refine our grains, and what happens is we're going to have, great casting, and that's the idea. And after a while, the grain refining effect fades, and so you got to pour quickly. And again, that's completely crazy tough because here's all that happens. In your bulk melt, you got millions of these oxide films that are in the melt from the transfer practice. And they're floating around, stuck in convection currents. They're all neutrally buoyant. And these are the ones that we couldn't float out with any kind of rotary degassing. We add the titanium and the boron. The titanium sticks to this oxide film, which is predominantly alumina or aluminum and magnesium. And what happens is it makes it heavy, and this thing sinks to the bottom. Well, guess what? After a while, it starts getting kicked up again by convection currents, and it starts bumping back into the melt, and that's your reduction of properties. So the initial increase in properties is the fact that these oxide films sedimented out, and then you tapped out, and this crap was still sitting at the bottom of your pot, right? This is the real key. Now we can get to things like strontium. Every single conference you go to, people are having arguments and debates about strontium, and everybody's doing their own study on strontium. And part of the failing, if we want to talk about the hilarity of the the situations that humans set up, for example, like the AFS, where, we have all the greatest intentions in the world to create an organization that's for the advancement of technology and foundry. But here's what we do. We take this group and we break it up into 13 separate divisions, and each division has its own committees and subcommittees. And so what you get is everybody working on their own, everybody doing their own things, and everybody doing all the same thing, and nobody talks. This is called conquer and fail, divide and fail. This is the Tower of Babel strategy, right? There doesn't need to be all these different subcommittees. Everybody's doing each other's work. I was just down at Cast Expo sitting through a paper, and I saw the same paper 10 years ago, but by a different committee. And so what happens is we just keep spinning around like retarded dogs chasing our tail, because we're not breaking these things down, having conversations, and working together. And not only that, but we're not working with theory. So let's talk about what strontium does. So in aluminum, for example, and the most common alloy in aluminum is A356. And so what we ended up happening is we've got aluminum, and we want it to be a little bit stronger and harder. And so we add some silicon. And the silicon forms some kind of phase that takes place. It's kind of a mechanical mixture. And what happens is we say that, well, if you take a look at the microstructure of the aluminum, and if the aluminum forms in these needle-like shape or this acicular type shape, what happens is since the silicon is in that form, that silicon is embrittling the metal, so we get really poor ductility, right? So the idea is, well, if we add a little bit of strontium, the strontium results in the formation of silicon that's nice, round, and globular, right? That's the prevailing theory. However, that isn't really what's taking place. So let's take a look at what's happening and why silicon forms in acicular needles in aluminum. Guess what we're going back to again? Bifilm. Here's your bifilm in solution, and it's floating around. And now we've got a seed for nucleation. And there's silicon, and it needs to start to grow. So it nucleates on the bifilm. And as it grows, as the silicon grows, the bifilm starts straightening out, and straightening out, and straightening out. And what we see now is this little microscopic 1 or 2 or 3 atom thick oxide film, obscured and invisible to what we're looking at with the naked eye or standard reflected light microscopy, and a great big giant acicular silicon needle. And we say, well, holy shit, the reason why this alloy is brittle and the reason why it has poor mechanical properties is because this acicular needle is responsible for that, but it isn't true. The needle is only acicular because it grew off of this oxide film. What happens when you add these rare earth elements like strontium is they form preferred nucleation sites. Preferred nucleation sites for the silicon. So the silicon starts to grow off of the little strontium that's in suspension now, and that starts to grow and forms a nice round ball of silicon. Now, the reason why adding strontium results in increase in porosity is because now these oxide films remain floating in suspension, and now what happens is they start to open up and they form the porosity in the casting. And so all we're doing is flip-flopping them, right? And so this is that delicate trade-off and this delicate balance. And what ends up happening now is that if you move towards bifilm theory, instead of using like 200 parts per million strontium, and if you have good melting practices, and we can never get all of the oxide films out yet because we just don't have the equipment and these kinds of things yet, you can use something like 10, 12, 15, 30% strontium and produce results that are never seen before, that no labs have been able to generate, even in water chilled molds and stuff. Where at the foundry here, I don't know if you guys have seen, but we get 10 to 20% elongation is normal. Usually 17, 18, 15, 16, 17, 18, 19, 20, every single day, all the time, right? It's only that simple, strict manipulation of that practice. And so now you start piecing together, well, if all those things are working, then what do we need fluxes for? Well, you don't, right? I mean, these things are just poisons that companies need to find a reason to do something with them. If you're not entraining the bulk oxide into the melt, then you don't need to use these poisons to begin with. And in fact, when you add the poisons, you just add terrible problems anyway. So imagine a situation where you aren't using drips and you aren't using vacuums and you don't need any fancy new equipment. And all you're doing is using less of everything and producing, results orders of magnitude above everything that's been experienced. This can happen, and it can happen every single day. And the practices that we've developed since 2008, when we really looked at building design heuristics and practicable methods to be able to use conventional tooling, conventional molding practices, and literally convert this overnight, ends up being a situation where anyone can do it any single time, and all you need to do is be able to open up your mind and get rid of the voodoo that you learned during the course of your history.
I wonder if we could take the last 10 minutes for some questions from the participants. Is that okay?
Yeah, absolutely.
I will let it up to you.
All right, shoot.
Well, I have one about it, and I can start this off. Hopefully everyone's going to, if they're going to ask questions, they'll remember that their mics are muted, and please feel free to unmute those at any time. As far as can you share the calculations you're using for your down screws and the amount of taper to get the naturally bottom filling or naturally gating system?
So in the thread, in the Vortex gating thread, I put a sample calculation sheet of the CAD that I assigned. And the calculation that I used and the definition of the variables is on there. And I designed the use of that formula to make it really, really simple and include every variable that anybody would need for any type of foundry and any alloy. And so it's in the thread already.
Oh, fantastic.
Yeah.
So you mentioned, if there's not any other questions,
There's questions in the chat.
I see the power. Someone's asking if the PowerPoint presentations would be available.
Do you guys want me to share the PowerPoint presentation I just showed? Was that the question is?
I think that's what the question was, yes.
Okay, I'll post it in, I'll post it on the, yeah, I'll post it.
There's other ones too.
You mentioned nickel, aluminum, bronze.
Yeah.
Which is a really interesting topic in the cleanliness of that. And I think that you poured quite a bit of nickel, aluminum, bronze with the naturally pressurized systems and
Hundreds.
Gates.
Hundreds. The main supplier to the U.S. Navy in your country makes all of their castings with my engineering. So I do the engineering, I do design work, simulation, build the patterns, and ship it to them. They mold or ship.
Now when you say main supplier, you talked about Newport News?
As you might imagine, I can't tell you.
That's fine. That's fine. Are there other questions out there? This is a great opportunity to ask Bob those questions.
And I'm only going to take my shirt off for a tip, just to clarify.
There was like several questions in there, Joe.
Here, let me open up the chat then.
That's
I'm going to be like one of these gamer YouTubers that my son watches all the time.
Bob, can you open up the, well, these are all privately. Let's see.
Can I which one? Yeah, I've got the chat. Yeah, I've got the chat. All right, so here we go. From Viking Pumps to everyone. If the max critical meniscus velocity is known, could a mold be designed without shrink? The shrinkage component, the volumetric contraction requires feeders, right? Now, here's the thing, is that most shrinkage defects that are assigned as shrinkage are actually unfurling of oxide films. Castings that are made that are poorly fed with no oxide films will generally experience surface sinkage or cavitation, or the generation of internal residual stresses and not open up as voids. However, a casting that's polluted with oxide films, even if it's fed properly, will tend to open up and look like crap. So I hope that answers the question. PowerPoint, yep, I'll post it. Is it always preferred to have the part in the coat? You can only fill metal from the bottom up. And so you need, if you're going to do these kinds of systems, you need a 3-part system or a vertically parted system, or you need to be really creative and get the metal to the bottom of the casting in a 2-part system. And so for simple like match plate or a rolling loop or a coat, these coat drag molds, I've got designs that can accomplish that almost every time as well. So yep, those designs, but the metal's got to come from the bottom and it can only go up. And it's preferred to come up and not from the side and up, if you understand what I mean by that. How do you recommend filling low pressure machines without oxide creation in the furnace pot? Well, you're going to get oxides in the furnace pot. You've got to get them out, or remove a transfer mechanism, and just don't do that. And what we're always going to hear for the last 8 years since John started doing this is people say, well, I can't just redo my whole molding process. And I say, why the hell not? These practices were invented by monkeys no smarter than us. We change them. This is what we're here for. What are we supposed to just carry on forever? So that's, do I do site visits? Hopefully you meant site, S-I-T-E. I'll do a site visit if you're a pretty girl. We can Skype privately, but site visit, yes. Anybody's welcome any single time. And a site visit, hit me up privately and we'll see what we can work out. Anyone else? More? No, that's it. Outstanding presentation. Oh, well, thank you guys. I'm so happy to tear up. Anything else?
Thought it was a great presentation. You didn't get a chance to get into the Trident gates or any of the in-gates to the castings. Maybe in the future you would, if this experience was good for you, maybe you would consider doing another presentation webinar.
Yeah, 100%. We've got, every time we start branching off of this core topic, it's 2 to 3 to 4 hours of hilarity. So yeah, anytime.
That sounds great. We're right at the end of our time. If there isn't any more questions, really appreciate the presentation. I know that we had, for your information, we had 50 different participants on today. So you had a pretty wide audience. I think you have a couple more questions coming in.
I've got, they're just comments. They're just giving you pats on the back. I want to leave you guys with a couple things. And then we're going to end it there. So I'm going to go over a few things. I'm just going to hang up. Just so we know, all right?
Very good.
Just give me a second. All right. Tell me when you can see it.
We can see it.
All right. Here's a quote. Keep these in mind, guys. Behind it all is surely an idea so simple, so beautiful, that when we grasp it in a decade, a century, or a millennium, we will all say to each other, how could it have been otherwise? How could we have been so stupid? John Archibald Wheeler. All truth passes through 3 stages. First, it is ridiculed. Second is violently opposed. Third is accepted as being self-evident. Arthur Schopenhauer. A long habit of not thinking a thing wrong gives it a superficial appearance of being right and raises at first a formidable outcry in defense of custom. But the tumult soon subsides. Time makes more converts than reason. And that's all I've got for today. Thanks, guys.
Very good. Thank you.